All right. How many of you will be writing out notes by hand, like in a standard notebook, a big portion of the class? Okay. All right. So those of you who will be writing out notes by hand in a regular notebook, flip to some page in the future in your notebook. 5 pages, 30 pages, 50 pages, some random number. All right. All right. And write in your notebook, what does this all mean? Question mark. All right, so now you've entered into a pact. When you get to this statement in your textbook of what does this all mean, you have to raise your hand and stop me, and you have to ask the question, what does this all mean? And I will pause what I'm doing, and then I'll try and come up with an answer. So I encourage you to ask this question regardless of where you're at in your notebook, and if you hit that mark. But it's just a kind of artificial way to break up the class, and every so often we'll have this question asked, and we'll take a little pause and try to connect it to something. Okay. If you blow through this, if you notice a neighbor just starting before what does this all mean, and by the end of class he or she is behind what's this all mean, point them out, and we'll do some sort of public shaming or something. Okay, so we have about 13 minutes left. Any other logistics questions? Yes?
So the final answers to the homework of that week will be posted on Monday or Wednesday?
Yes. Yep, it'll be pretty simple. It'll just be like whatever you would usually box in your answer. That'll be it. And so it's your job really to fill in the blanks in between. So. Okay. Oh yeah, well, that reminds me, there is a grader for this class. I've had people ask this question before, and I never give the answer. There's a grader. I do not reveal his or her name. Okay. The reason for that is because when I was an undergrad at Ohio State, I was a grader for a class, and someone I went to high school with was actually in the class, and he found out that I was the grader, and he started to try and extract information and other things in terms of helping us grade out. And that's it does not put the grader in a good situation because you are peers, right? Okay. So I try and protect the identity of who that person is. So there is a grader who's an undergraduate student, but his or her name will not be revealed by me, at least. Okay. Any other logistics questions? All right, so central theme of this class is systems integration control. And so what this really means is higher order systems. So in 3260, you may have gotten through maybe third, fourth order systems, etc. These are typically just a single system that you can model by third or fourth order models. And you focused a lot on solving the solution for that system, right? So you had some sort of system, you had the input, you wanted to know what is the solution in time for that system given that input, right? So that was the focus 3260. The focus here is a little bit different. We're oftentimes talking about orders of systems greater than second order, and we're also talking about multiple systems interacting with each other, which is going to inevitably blow up to like 6th, 8th, 10th order systems. And we're going to stop focusing so much on what is the exact solution to that differential equation. We're going to focus more on general ideas of behavior for the system. That's going to be the major transition. So when we talk about higher order systems, so if we have a second order differential equation, say for instance a mass spring damper, like this, right? This would be a second order differential equation. We're going to be talking about differential equations that are of higher order. So say, for instance, we have a bunch of coefficients and then also orders of differentiation with respect to time, and also higher orders on the input as well, which we could have not what I want to say. Okay, so this would be, say for instance, this is an nth order system. This would be a n x to the nth derivative plus a to the n minus 1, x to the n minus 1 derivative, all the way up to x to the 0th derivative, right? So looking at higher order systems, as the system goes up in order, it gets much more difficult to solve the differential equation by hand. At a certain level, I would say, for the sake of an undergraduate class and the time you have allotted for quizzes and tests, it's possible to do by hand. So we're not going to focus so much on solving this by hand, but looking at more or less how they behave, and trying to just come up with some descriptors on how they behave so we can understand how systems behave. Also, we're going to have interconnected systems. So say, for instance, we have the system that's described by this differential equation. We'll call this 1, where we have the output, x. All right, this is what we would normally solve for in a differential equation, is dependent on the input. But we're going to complicate things. And we're going to have also the input is formed by a differential equation. K equals 1 all the way up to, say, uppercase K. And this is going to be a product of some sort of function in time and also the output itself. Okay, so kind of briefly what we have here. We have system A, which we can describe by, say, for instance, its input and output. We'll just call it system A. Input of U, output of X. We have now system B, which has two inputs. It has this forcing function F, and it also has X. And then this becomes the input to system A. Okay, so we're going to try and understand how these systems are all interconnected or integrated. The name of the class is Systems Integration and Control. And how do we make sure these systems, when they're all put together, behave in a favorable manner? Right. Okay, so how do we design interconnected higher order systems to behave how we wish them to? And then a simple example is cruise control. So the cruise control example, I'll get to this in a second. I guess in the last 5 minutes we'll talk about cruise control. Cruise control is probably the, I don't know, it's not definitely not the simplest example, but it's the example you probably are all familiar with of systems that you have multiple systems working together to achieve some sort of objective. So who has a good idea or general idea of how cruise control works? How does your cruise control in your car work besides just you push the button and it goes? What's actually happening under the hood? Yes, in the back. Yeah, just walk me through the steps of kind of what the individual parts of a cruise controller does. Sure, okay. Okay. Right. All right. So just so I heard you correctly, you're talking about how much, you said how much vacuum the engine has, is that what you said? Okay. Okay, and it's the seventh offering of teaching this class. That's the best answer I've gotten so far, so congratulations. I did not know about this whole engine vacuum thing. I learned something new today too. So what was described is basically this loop down here. Okay, so, sorry, what's your name? Connor. So what Connor described is that you have some sort of sensor on the system, right? So that was the first thing he talked about. So he talked about a sensor, and this is a speed sensor, right? Okay, so you have a speed sensor in your car, so your car has an engine control unit on it, and it needs to know how fast your car is going if it wants to do cruise control. Right? And so you have a sensor on this. This, for all intents and purposes, this acts like an algebraic equation. But strictly speaking, this is actually a differential equation. The sensors have dynamics to them. But basically, you have a system in here that measures what your speed is. So you have an actual speed to your car, which is more of a notion. All right? So you have your car is going down the road. It is going, say, 65 miles per hour because you're a law-abiding citizen, right, on the highway. And you have a sensor which measures that, and it may be a good measurement, may be slightly off, but anyhow, that's the best information you have about the speed of the car. Right. You also have your set points. So your set point, we'll call in this class a reference, and this is what is your desired speed of your car. So in the engine control unit, as described, you're always comparing the set point to the desired speed. Right. So this is, in terms of block diagram form, this is time. Your set point would be 65 miles per hour, so you don't get pulled over. Everyone here does this, right? All right. And then your actual speed, as measured by your sensor, is going to be something slightly different. Right? So say, for instance, at a certain point in time, you were going 3 miles per hour slower than 65 miles per hour. Your car was actually going 62 miles per hour. Here's your current speed, as measured by your sensor. And so what's coming out here is the difference between those two, and that's 3 miles per hour. So the difference is actually 3 here. And so what this does, it goes into the engine control unit. As described by Connor, it uses a bunch of other factors as well to try and understand, is it going up a hill, going down a hill, etc. But then this goes into what is your cruise controller, which is an algorithm that's built into your car that translates how do you take a 3 mile per hour difference and then turn that into a throttle decision. And so this is given by a differential equation. Okay. So you have algebraic equation with a basically subtraction, which is another algebraic equation, interacting with the system, which we model by a differential equation, which then goes into the actual car, which is the gas pedal control element, and the car itself. So the car itself has dynamics associated with it as well. It looks like, essentially it looks like a mass and a damper is what a car is, a very simple model of a car. Okay. It has disturbances, so as Connor's just describing, it's going up a hill, down a hill, etc. These all play in terms of how the system responds. And this is, again, since this has dynamics, based off of Newton's laws, this is a differential equation as well. Okay, so we have differential equation interacting with the differential equation through an algebraic equation, reacting back into the input of the cruise control, which is the differential equation. So two systems described as differential equations, two algebraic equations, everything works together, and somehow you have to make sure this thing behaves in a favorable manner. So in the last minute, just a description of what a favorable manner is, I'll talk about what would be unfavorable behavior. All right, so say, for instance, I guess to say, you as a person can do cruise control yourself, right? You can look at the speedometer, and you've driven before, so you have a general idea of how much you need to change the angle of the accelerator to hit 65 miles per hour, right? So we need to make a car do exactly the same thing, but we need to make it do it in a favorable manner. So in this class, you're going to look at instability, and you can make this differential equation here, this one right here, behave in a very unfavorable manner if you do it incorrectly. So unfavorable would be if you, as a personal cruise controller, you saw a 3 mile per hour difference in speed, and your reaction was to slam on the accelerator as hard as possible. Right? That'd be a very bad decision. You would never do that, but we could accidentally make a engineered system do that. And if your reaction was like, oh, I'm going 10 miles per hour too fast, hit the brakes, right? You're going to have a very dangerous system, right? So we need to make sure that we're having systems that respond in a favorable manner. That means transitioning between speeds in a very smooth manner. We're going to talk about this in terms of pole locations and oscillations in our system, right? You don't want a cruise controller that's just always going above and below 65 miles per hour, right? So more of that on Wednesday. I'll get the books and everything posted to Carmen. If you have any questions, please email or, sorry, put it on the discussion board. See you on Wednesday.